Okay, welcome to Linear Algebra Tutorial 1. Today we'll go through question 7 to 11 if that is possible. And now I'm going to share the screen. Okay, I hope you are seeing the screen. So today we are going to go through question 7 to 11. And then let's just go through the first question 7. In this question, basically he asks us to construct a matrix A that is a 2 by 2 matrix. And he says that the solution AX equals to 0 is not unique. It is a line through 2 points, the origin as well as 4 by 1. Okay, so let's construct A first. In here, well, he's asking you to do A, and later on you realize that A looks like this in the bottom. It is the 2 by 2 matrix. The values are unknown now, so we will leave A to be something like, some AB. And then you'll be wondering, what about this guy? And then some of you will say CD. But actually, because he's going to tell you later on that the solution of XY is a line. So what happens is that if it is a line, the second row of the equation will actually be dependent on the first row. But so later on, I'm going to give you a solution that is AB as well. And in fact, that will be the answer, or it'll be something like AB, some constant times A, some constant times B is also a possible 2 by 2 real matrix. But let's try this, it's easier. Now, why is this so? So why does the matrix look like AB and AB? And it is because it says that the solution is a line. All right. Now, but we don't care about this first. Let's go through that the line goes through 4 by 1, x equals to 4, y equals to 1, and the origin, which is 0, 0, so which is on the left-hand side. So let us study a line that goes through the origin and 4, 1. And what would the equation be? Then you can say that, all right, we inspect this line, and y is equals to 1/4 x would be this line. What do you call that? How would we write the equation for the line? Now, if you are given y equals to 1/4 x, how would you write in matrix vector form? So what I did was that we don't like 1/4, so we basically multiply the left-hand side and right-hand side by 4. So we have 4y equals to 1x. We also don't like to write y equals to x because we want to do a matrix vector notation. So what we then do was that we write it as minus 1x plus 4y equals to 0. Once we have this, then we can write it in the matrix vector notation, which is implying minus 1, 4, xy is equals to 0. So we went from an equation, to the vector or the matrix vector representation, minus 1 for xy. So in fact, when you look at this carefully, it is nothing but minus x plus 4y equals to 0. Now, we have already found minus 1 and 4. But later on, you realize that I can actually find other values for this to be true. In fact, any values along this line can be the x and can be the y. Why so? Well, we know that this is our equation. Minus 1/4 x plus y is equals to 0. Let us find another x. And in fact, if we say let x equals to 2, then y is equals to, so minus 1/4 times 2 plus some unknown y is equals to 0, and y is equals to then you say it's half. So when x is equals to 2, y is equal to half. So how does that relate to our line? Let's look up. When x is 2 is here, and when we project up, so y is half. Okay, so in fact, you can keep on putting any values that you want, and as long as it's on this line, this equation would be solved. Okay, and then if you understand from that angle, then you say that, oh, okay, there are plenty of x, y that will solve this equation. And that is why we also say that to solve, when this equation has not a unique solution, has infinite solution. All right, so so this is our little examples of plugging in different x and y, and you will see that, okay, as long as it satisfies that the x is alpha and the y is minus 4 alpha, it will solve this equation. Now, what about the second row? I claim that the second row of the equation A is exactly the same as the first row. So why is this so? Now, remember that, all right, we start with what we think we know first, which is that, let's put the first equation and the y here, sorry, the b here. This is the matrix A, and this is the entries of B. And we also put the second equation to be exactly the same. And then we begin to solve using Gaussian elimination. And when we solve, then we say that, okay, this is easy because we are doing R2 equals to R2 minus R1. So then we have all zeros here, and we are done. So this is the reduced row echelon form. And then we circle the pivot, and then we only have one pivot, and then one pivot, and therefore we have one free variable. And because we have one free variable, the solution is infinite. Okay, so, and then when we say the solution is infinite, actually in this interpretation, then the answer is that the solution is a line because it's not a single point in R2. So we have come one big round to go from that little graph to see that actually the red line is all the solution. And when we put it into matrix form, we also realize that one pivot, one free variable is also telling us the same thing. Okay. So with that, I think at least the part A is done. We now know this free variable thing. Let's go to the second part of the tutorial, which is we're then asked to find a vector B such that the solution is not a line parallel to the first equation. Okay. So that this red line on my right hand side, okay. Now this red line on the right hand side is the first part A. And then I'm going to construct another solution, which is the green line. And why would we have the green line parallel to the red line? And then we'll figure that out. Once we figure that out, we'll be able to answer the question. Okay, first we generalize. Just now we put alpha is 1, and therefore this is 1 minus 4, 1 minus 4. Was it 1 minus 4? Okay. Now, if this is the first row and this is the second row, each row came from an equation, then the corresponding AX equals to B, the elements of B, because the left side is the same, the right side B must be the same. So On the right side, we must have z, the same z for the first one and the same z for the second one. It must be the same. And if they are the same, then when we perform Gaussian elimination, we'll get 0, 0, and then z minus z, then we'll get 0. So everything is okay if the equations are consistent. But if the equations are not consistent, when we try to eliminate this row, then the right-hand side is not equals to 0. And then the equation becomes inconsistent. Let us first think of when the equation is consistent first. When the equation is consistent, then what happens is that the right-hand side will be 0, 0, 0 after Gaussian elimination. And then we have some value z here. Compare that to the previous slide. Our right hand side was 0 because it was ax equals to 0. Now we generalize, it will be ax equals to z, some z. All right, let z equals to k first. And then we try to solve this equation. When we solve this equation, what we do is that we take alpha multiplied by x minus alpha multiplied by y equals to z, which is equals to k. So we get this equation here. Alpha x minus 4 alpha y equals to k. We just want to solve. We don't care about alpha because alpha is some variable. And then we just let alpha equals to 1. So we x minus 4y equals to k. Then we write the equation in terms of y so that we can plot the graph. And then we recognize that, hey, wasn't this the 1/4 x that we are having in the part 1? And which is, so the only interesting thing that happened was that the z, which is now k, is divided by 4. But what does this mean? And actually, what we see is that this is an equation that is 1/4 x plus some constant. Now we go through that constant and we now plot this offset, which is the green line. And you'll realize that, oh, okay, when we have ax equals to b and when b is not equals to 0, it is another line parallel to the red line, shifting up and down. And that's the interpretation of that little z on the right hand side. It is the offset from the red line. And the green line will be parallel to the red line because it is always 1/4 x. That's why it is parallel. So it is the offset that is only shifting it up and down. So the solution of the green line is still that green line, any point along the green line parallel to the red line. So the question asks, is there any b that we can choose such that the solution is not a line parallel to ax equals to 0? And the answer is yes. If b doesn't appear as z, z. If b appear as z and not equals to z, then during Gaussian elimination, the second equation would be something like this. Alpha minus 4 alpha z 0, 0. And then it'll be some value, whatever you want it to be, b2 minus z. And if this guy is not 0, this whole equation, this whole row is inconsistent, showing us that 0x plus 0y equals to some not equals to 0. And therefore, we can say that the equation is not the equation is inconsistent. There is no solution. Okay, so this question, let's go through this question one more time. And let us figure out what is he trying to do in the second part. In the second part, he's trying to ask you to understand that actually when the equation is consistent, the solution will always be a line parallel to ax equals to 0 in this example. And it will not, and if the solution is inconsistent, if the equation is inconsistent, then there is no solution. Okay, so I hope that answers question 7. Any questions, guys? Okay, let's try some more. All right. Let me move this away. Now here is in question 8, tutorial 1. We are given a 3 by 3 matrix A. And this is the condition. AX is not equals to Y. So you have a 3 by 3 matrix. You have a 3 by 1 column vector. So this is A and this is X. And when you try to multiply A and X, you will get a 3 by 1 column vector. And you hope that it is Y. But in this particular case, you cannot find a solution. A solution means that there is no X that when you multiply with it will give you the desired Y. And why is this so? You say that the left-hand side is a 3 by 3 matrix multiplied by a 3 by 1 column vector. The elements we can choose. Why is there no such Y? All right. Now let's try to understand it from a very simple, naive example first. If I give you a matrix 1, 1, 1, 1, 1, 1, 1, 1, 1, and then I say X, Y, Z, up to you to choose. And then if I give you 1, 2, 3, then you realize that no matter how you choose X, Y, and Z, there is no way you can get 1, 2, 3 out of columns of all 1. Then you say, well, what about the second column? It's useless because the second column is the first column. In fact, I can even cheat. And then you say, what about the third column? It doesn't matter because the first column and the second column and third column actually lies on the same line. Gives you no new information. So no matter how you try, this thing doesn't work. But so this is only a concrete case, so it's easy to appreciate this. How do we generalize? Well, you can use Gaussian elimination. So what you do is that you take this whole matrix and you put it as an augmented matrix. So you have A here, and you have B here, and you start to do Gaussian eliminations, and then you hope to find 3 pivots. And if you find 3 pivots for 3 variables, then you have a unique solution. Okay, so let's try. But he says that, in fact, he's not even asking you to try. He says that there is no solution. AX is not equals to Y. So now let's interpret why is there no solution. It is because in Gaussian elimination, in this example, I have 3 variables, but I don't have 3 pivots. I have 1 free variable. That's one. Another interpretation is that that there's no linear combinations of A, which I just shown you to produce Y. And if there is, so the solution Y can be no solution, like in what I have just given you, or if there is a solution, it'll be infinitely many solutions because the answer has a free variable. Okay. Now, so in a no solution case, how do we identify is that during Gaussian elimination, the bottom row after we have do Gaussian elimination, the left hand side is all 0, but the right hand side is not equal to 0, giving us the equation of 0x plus 0y plus 0z equals to some value that is not equal to 0. So the equation basically is inconsistent. All right, let's try this simple example first. Now we have an A, and we are going to try to solve for this. And immediately it's obvious to you that the second column and the third column are identical to the first column, or This is totally dependent on the first column. It's the same as the first column. Let's solve. So basically, R2 is equals to R2 minus 2R1. R3 is equals to R3 minus 3R1. So we get rid of the all zeros. We get rid of zeros. So this is B minus 2A. Okay. C minus 3A. Okay. We circle up. There's a pivot. We're happy. And now we can inspect these guys. Now, for this equation to have a solution, this guy must be 0 and this guy must be 0. For these equations to have no solution, then as long as these are not equals to 0, these are not equals to 0, we can say stop. There's no solution. The equations are inconsistent. All right. Maybe the simplest way to appreciate inconsistent equation is this. Is I give you this equation. How does it look like? It will be 1x plus 1y plus 1z, because you take this, multiply by this, equals to a. Now, I will also take this as 1, 1, 1, just for fun of it. And I will just call this a is 1 and call this b is 2 first, just for fun. And then now let's try this, multiply by this. I get second equation 1x plus 1y plus 1z. In the first equation, I got 1. Second equation, I got 2. And of course, immediately you know that, hey, first time you gave me this equation was 1. Second time you give me the equation is 2. Doesn't agree, it's inconsistent. But when you are looking at on the graph, it is because the answer of this, or when you sketch this graph, these two graphs are parallel to each other. They do not cross. They do not meet. There is no solution. They are parallel. So in fact, the interpretation is that the right-hand side, these guys are offsets, allowing us to move the solutions up and down and parallel to each other, and that's why they never meet. That's the interpretation. Okay. So anyway, so we are back to here, and we have one pivot and two free variables. So how do you write the solution? So we start from this equation. This guy is multiplying by x, multiplying by y, multiplying by z is equals to a. Here, let's ignore this and assume it's 0. So we can write it like this. X, because 1 multiplied by x, 1 multiplied by y, 1 multiplied by z is equals to a. That's all we are given. There's only one equation, because the other two equations are useless. They are just multiples of each of the first equation, and therefore that's why we got rid of them in Gaussian elimination. Okay, but we are here to write the solution. So how do we write the solution? Oh, well, we already know this. So we now want to put our variables x, y, z on the left-hand side, and then we can, write the equations with respect to x, meaning x equals to constant a minus z minus y. Okay, the second one, the same. A minus x minus z. The third one, the same. A minus x minus y. Then you say, it's okay, I haven't done anything yet. I've just shifted the equations around. But now we can write it in this way. This guy, xyz, is equals to this guy. Okay, still nothing much is changed because all I did it this way. But remember that y and z are free variables. Free means that it can be set to any value. Let y be k1, z be k2. So what happened? Then we can write it as equals to a sorry, let me Because x and y are free, we can set it to 0, of course. So if we set it to 0, we are done. And then we have this guy. What about the others? Did I make a mistake? Let me see. I see. Okay. I'm going to use this slide instead. So the only interesting thing was, I always make this mistake, sorry. When I'm in this equation, actually y and z are free variable. So I can actually ignore this equation and I can write y is equals to k1 and z equals to k2. That's the trick, because they are free variable. We then say that if y is equals to k1, I can write k1 here, z is equals to k2, I can write k2 here. So from this equation, I will proceed to have this equation. With that, I can then reduce it to x, y, z equals to the first row is this one, the second guy is this one, and the third guy is this one. With that, I can then reduce to a 0, 0 plus, and then I'm going to bring up this guy and this guy. So what am I basically doing? I'm writing x, y, z in a parametric form because I'm using free variables of k, different k's, k1 and k2, to multiply by this constant plus this particular solution to give the general solution of x, y, z. You can then ask, what happens if I set this guy to 0 and 0? This is one of the solution of x, y, z. What about if I set k to be 1? Then you get another solution, but the answer still remain the same, and so on and so forth. So in fact, the key idea is that these two vectors here, k1 multiplied by this first vector and k2 multiplied by this second vector, are called homogeneous solution because A times any of the vectors belonging to this set, the output is 0. It doesn't matter. It is the homogeneous solution. What about this guy? This guy is one particular solution. And the homogeneous solution plus the particular solution is called the general solution. So that is for question 8. Okay, so let me just go through. Now, he then asks you, the second part of the question is there a z such that ax equals to z is unique? And the answer is no, because once you have a free variable, it will never be unique. Yeah, so that's the answer. All right. Okay, any questions so far? Now, in fact, if you go through my YouTube channel for each of these questions, then I explain it maybe in also a slightly different way, but the answer should be the same. Okay, so with that, let's go through tutorial 1, question 9. Let's read the question first. We are given two vectors, these two vectors, and when we are asked to find out whether the third vector given to us are linearly dependent. So what is he asking for? Let us write the three equations first. this is the first vector he give us. This is the second vector he gave us. And then he says that this third vector, I draw in a square, is he dependent? Are they linearly dependent? Basically, he's asking us, is it possible to construct the third vector using linear combination of the first two vector? What does linear combination means? It means that let us use a scalar. X is belong to R, means X is a real number. Y is a real number. You can choose any real number you want. You multiply by X, you multiply by Y, the first two vectors, you add them up, and as long as it equals to the right hand side, it means that the third vector is dependent on the first two vector. So the easiest, the most trivial example I can give you is this. If I give you 1, 1, 1, let's say 3, 4, 5, and then I ask you, is it possible to find 4, 5, 6? And then the answer is obvious because it is nothing but 1 times the first column plus 1 times the second column. Okay, so therefore 4, 5, 6 is dependent on the first two columns. Now, so that's the problem we want to solve. Can we find? And because and one way to find is, of course, we always write it in this form in a matrix vector notation, and then we can write it in the augmented matrix notation, and then we perform Gaussian elimination. That's the trick. And when we perform Gaussian elimination, you'll reveal the pivot, and then if we have two pivots, then the solution is solved. So let's try. All right, we have this is A, B, and we perform elementary row operation. We start with, oh, in fact, I made a mistake. Okay, but never mind. Here, when I began, I didn't like H to be here. So I changed my third row. I moved my second row to my third row. And I moved my third row to my second row. That's all. So elementary row operation, if you change row, yes, no problem. I then perform R2, the second row is minus half of R1. And in fact, then I realized that, oh, okay, the second row is actually half of the first row. Therefore, we immediately get a row of 0. Okay, fine. Then, of course, we don't like zeros to be there, so we change back the third row back to the second row move to the third row, and we are in this equation. All right, once we are in this equation, then we need to interpret. Okay. Anyone can help us interpret? Okay. Now let's try to interpret, because when we finish interpreting, we'll know how to solve the problem. First is, the question was, is the third column B dependent on the first two? Hey, we got one pivot, we got two pivot. So even though we have R3, but we still have two pivots. Wow. Not only that, the third row is all 0. Means that we are fine. Means that we can do something like this. For example, how do we interpret? If this is X, this is Y, and this is Z, our equation is, if we look at this row, is 0x minus 5y. Sorry, let me think. There's no Z. 0x minus 5y is equals to h plus 16. What about the first equation? 2x minus 6y is equals to 8. The first row can be solved. Once I have given you h, the first row y can be solved. Once y is solved, we can substitute in here, then x can be solved. We're safe. Any choice of h, any choice, regardless, can be formed by the first two columns given to us. Okay? And therefore, the answer is yes. The vectors, the third vector is dependent on the first two columns for any h. So that's the interpretation. Now, maybe you want to ask, it's very strange. I have R3, and yet I only use two columns to solve for my B. So what does that mean? So if the interpretation is this, the first column, the second column, their linear combination is, let's say, like this. Maybe it is a plane. Can? So their linear combination is a plane on R3. Let's call this X, Y, and Z. And what about this guy? Where is he? Actually, depending on the value of H, and regardless of value of H, he is actually sitting on the plane. Different H gives you different point on the plane, but he is still there. And that is why we can find two pivots to solve this equation. Okay, so this is the answer. 8H and 4 is a point onto the plane spanned by the two columns given to us. So that's the interpretation. So actually with this picture on the bottom here, this picture, then you understand the span of the two columns. Okay, any questions so far? No? Yes? Okay, chat. Isn't the question asking if all three vectors are linearly dependent? Yes. So the question asks, are they linearly independent? No, I think no. Let me check. The question asks, find which are linearly dependent. But my interpretation of this question is we're given these two vectors and find whether the last vector is dependent on the first two vectors. That's how I interpreted it. Because there is no way, yeah. I'll give you an example. If the question is, are the vectors linearly dependent? This guy and this guy are definitely not linearly dependent. You can never find a constant such that y times this guy is equals to, let's say, this guy. There's no way. Can? So the question, we always, the typical questions for such kind of theory is, I give you vectors, ask you to find W, which is the span of the vectors given to you. And then I give you another vector called B, and then I ask you whether B is in the span of, and then I ask you whether B is in the span of the given vectors. That's the typical problems we want you to solve. Okay. Now let's try some more. Yes, some more questions. Okay. Okay, thank you, Tayan. All right. Now, number 10 and number 11. So we are given E1 and E2. So this is E1 and this is E2. And whenever you look at, when you ever look at a vector that has only one and lots of zeros, then they are actually called the standard basis. Let me pull out wiki. And we like standard basis. And the standard basis are typically denoted by E. Basically, it has only one element of 1, the rest are 0. And the standard basis allow us then to sketch something like, what do you call that? The standard way we're going to sketch the world. So in the two-dimensional world, we always say this is E1 because along the x direction is 1. So this is x. And then E2 because along the x direction is 0, but along the y direction is 1. Okay. So we give you a basis that points first at one direction, and in the other direction is very interesting. It is perpendicular to the first direction. So E1 and E2 are perpendicular. Later on, you will find that the correct word to use is called orthogonal. And the notations typically for this standard basis is E1, E2. All right. Then the question says, E1 get mapped to Y1. E2 get maps to Y2 through this linear transformation T. So the lingo is this. T is a linear transformation with its input E1 and its output Y1. The same T acting on E2 produces Y2. So what about all this what do you call it? This very complicated looking notation. Here, when we read it, you'll be like T is a function such that, so the colon is such that it will take in R2, means that it will take a vector with two elements, x1, x2, for example, or if you prefer it, xy, up to you. Two elements. Here, the word R2, the word R is the real number R, the real. R2 means real times real. And what does real times real means? Well, okay, let's try. If I say x belongs to R, then you will say that x is a real number. So remember, a real number, I have 0, I have 1, I have 2, I have 3, minus 1, minus 2, minus 3, and so on. And any elements along this line is the real number. Now, then I say it's an element of R times R, or actually it is equals to R2. What does that mean? What does R times R mean? So it is a coordinate system. R times R means we introduce one more line perpendicular to the first one, and this is also R. So this is minus 1, minus 2, minus 3. R times R, a coordinate system with two axes. There are two elements. And then if I want to represent an element here, then it will be 2 colon 1, two elements. So that 2 also means number of coordinates in your vector. So this is 2 colon 1. This is 3 colon 1. So there are only 2 coordinates. So it's R2. So that's the interpretation of R with the number Rn, wherever n is. Of course, n is integer. Okay. Now, so we say that T is a linear transformation. So, all right. And then you say that, okay, let us find T of 5 minus 3. Now, the question is interesting because I'm only given T of E1, T of E2. And now I'm asked to find T of 5 minus 3. So what's the trick? So the trick is, he told us that the problem is T is a linear transformation. So what does linear transformation means? So we are going to say a linear transformation behaves like this. Okay, T of, let's call this alpha V1 plus beta V2. Alpha is a scalar, okay? So beta is also scalar. All right, so the word scalar here means, in our case, it's just the real number. It can be any real number. Later on, you realize that scalar can be complex number as well. All right, but never mind. We are interested in real number first. V1 and V2 are the vectors. And in our example is R2 in this example, okay? Now, linear transformation tells us that if we are given this guy plus this guy, it will look like transform of alpha V1 plus transform of beta V2. Okay, so the first big deal of linear transformation is this. It will break your problem into smaller problem. So alpha V1 plus beta V2 can be broken down, and we work on them separately. Okay, so that's a big deal. Huh? The second big deal is that that little alpha there and a little beta there can be taken out. Is equals to alpha TV1 plus beta TV2. Now, if all this from here, we can go to here, then this big T is called a linear transformation. Okay, so now you understand the word linear transformation. So once we have understood the linear transformation, we're going to use that principle, because we say that, hey, isn't 5 minus 3, sorry, is equals to 5 times 1 0 plus, not plus, sorry, actually is minus, actually plus minus 3 times 0 1. You say, yes, of course it's true. I break this into the sum of this. And isn't this guy E1? Yes. And isn't this guy E2? Yes. So I can write it as 5E1. And that I don't like the plus minus, so I just write minus 3E2. Wow. Okay, then I'm basically operating on this. And then remember that this is a linear transformation, so I can keep on breaking things down. And I can bring the 5 out. And I can bring the 3 out. And then this was given to us. TE1 is equals to this guy. TE2 was given this guy. Therefore, now we can do, and then we get the answer. Okay, so this is from first principle. You must understand what is linear transformation, and then we'll get the answer. All right. How about the other one? There's many ways to do it. In your lecture notes, it says, let's find the standard matrix representing the linear transformation. What's the standard matrix? This guy. Putting the standard basis, which is 1 followed by all 0, 0 followed by 1, and then so on and so forth. That means each columns have only 1 at the respective place. This is a standard matrix. Sorry, this is the standard basis. And then we perform the transformation on the standard basis to get the standard matrix. And then how do we get it? Okay, T operates on the first column to get you the first column. T operates on the second column to give you the second column. What was the first column? TE1. Okay, we read off. What was the second column? TE2. We read off. So if you want to work from this idea, all we are saying is put TE1, TE2 as a matrix. So this is the standard matrix of the linear transformation. We then use it. We have already found it. We use it on the new input which was given to us. So it becomes a matrix multiplied by a vector. You work it out, it is exactly the same. Okay, so the big idea that you want to take home is that you realize that the standard matrix, every column is the transformation of the standard basis. Actually, same idea. If you go through very deeply, we're doing exactly the same thing on the left as well. And that is why they say that all linear transformation can be represented as a matrix. Okay? Okay. All right. Now, let's go through the last questions. We are done. Any questions, guys? Okay. So in the last question, he wants to find the standard matrix of linear transformation for so there are two questions, A and B, and they are different standard matrix. Okay, the first standard matrix tells us that I am a 2 by 2, sorry, my transformation takes R2, a vector with 2 elements, and generates R2, a vector with 2 elements. It first rotates by minus 3 over 4 pi. Now minus here, rotate. So every time when you are talking about the word rotating a vector, you must be very careful. When you do it clockwise, they are positive angle. When you do it anti-clockwise, they are negative. When you're doing clockwise, they are negative. So here is given, ask you to rotate minus 3 over 4 pi, which is minus 135 degrees. He's asking you to rotate clockwise 135 degrees. After you have rotated, then he's asking you to reflect against the x-axis. Okay. So remember that we are asked to find the standard matrix. So the trick, of course, is that we will find the standard basis first, which is 1, 0, 0, 1. Then you say, why 1, 0, 0, 1? It's because he told us that the input was R2. That's why we choose 1, 0, 0, 1. If you told us that it is R3, we need to do this. And if you do R4, then you just basically have more of this. Now let's always try to think hard. He tells us it's R2. Why did I do 1, 0? Where's the 2? 2 is, one of them is that he is a vector with 2 elements. Why do I need another guy? It's because I need 2 vectors to span R2 space. And these 2 vectors must be independent of each other. But then you say, why do I choose 1, 0 and 0, 1? Because they are the easiest numbers that I can choose to span a space. Okay? Then if you ask, can I choose a basis like this? Maybe AB and then CD, can you? And then you say, what's the number of AB and CD? Well, as long as this guy is not a dependent, it's not a constant multiple of AB, you're fine. You can, both of these 2 vectors can be used to span R2 space. Okay? But then you say, wow, then you realize that if you want to choose easy computation, then always, use the standard basis. Later on, you'll realize that maybe you want to find a different basis, but there's another story altogether. Okay, now let's try. So we are asked to rotate. So first is let's perform transformation on E1. E1 is 1, 0. Where's 1, 0? So I draw X and I draw Y and I find my point 1, 0. I am told to rotate by 135 degrees. So I go here, I'm at point 2. I'm told to reflect across the x-axis, I'm at point 3. So the transformation of 1, 0 is equals to, and I read off, this is negative 0.707 and this is positive 0.707. Why? It's because the length was 1. And if the length is 1 and this angle is, I think it's 45 degrees, right? So then you can use the formula to calculate the two elements. Okay, so that is E1. And what about E2? Okay, so we try transformation on E2. Where is E2 again? E2 is x is 0, y is 1. So I'm at 0.1 here. I first rotate 135 degrees clockwise, I reach 0.2. I reflect against the x-axis, I get 0.3. I read off, this is 0.707, this is 0.707. So this is the answer. The transformation of E2 is equals to positive 0.707 for the first element and 0.707 for the second element. I put it all together. This is transformation of E1. This is transformation of E2. This is my standard matrix for the first question. The last question is the same. So the trick, of course, is transformation of the E1, transformation of E2, play with these requirements, and then you'll get the transformation matrix. Okay, so I think the details, you can watch it in the YouTube video for this question, but it should be quite straightforward. The thing that was not straightforward was I had this problem. When I was doing this question, I didn't figure out this. It reflects across the horizontal axis. That was easy. But it reflects through the line y equals to x. So the problem I had was this. Let's play with this again. Transformation of E1. E1 is 1, 0, which is this point. This point is horizontal axis is x is 1, vertical axis is 0. It reflects across the horizontal axis, means that nothing happened. Oops, okay, nothing happens here. And then it reflects y equals to x. That's the question, right? Let me see. Yeah, where's y equals to x? So this is y equals to x, a line that cuts diagonally across. It will reflect across there, means that from this point, you'll bring it to P3. Okay. So when that happens, then we can read off transformation of 1, 0 equals to 0, 1. The second coordinate, transformation of E2 is similarly gotten. And then you can interpret it as it's a rigid rotation clockwise 90 degrees, because you can see that actually what do you call that? The first point get rotated anti-clockwise by 90 degrees. This guy also get rotated anti-clockwise by 90 degrees. So in fact, the two axes is rotated by the equal amount. And if you check for any other point, they will also be rotated equally by two amounts. They are not stretched or whatever. They are all rigidly rotated by 90 degrees. Is it clockwise or anti-clockwise? Should be anti-clockwise, right? So I should write anti-clockwise. Okay. Yep, anti-clockwise. All right, I think with that, I'm done today. What I'll do is that I will also share this video up, and then you guys can jump to whichever questions you're not sure of, or you can also look at the video of individual answers. That will be easier. Okay, yes. For question 9. Yes, this is question 9. Yes. Because the last row is all, can I say that there are infinite solutions? Okay, first thing is this. So the gentleman asked, or the lady, Tai An asked, first is, yes, you are right. The last row is all 0. But can I say that there are infinite solutions? No, you can't. First is that no, because you see, we are only given 2 columns. Okay, therefore we have no free variable. We only have x and we have only y. And then we are asked that the last column, is he dependent on the first 2 columns? You see, a row of 0 is not that there are infinite solutions. Only when they are free variables. So this is not free variable. We have 2 pivots, 2 variables. There are no free variables here. Okay, that's how I think. Now, why then I say that it doesn't matter what h is necessary, because for any h that you plug in, this equation is true, and you can solve for y immediately. And when you can solve for y immediately, this y can be substituted upwards, and then you can solve for x. So there is a unique x and y for any given h. So it is not like there is infinite solution. It's not. Okay, Gabriel says, can we take the linear combination of all 3 columns and equate it to 0? Hence, yes, you can. That's another way. So Gabriel says that if we put these 3 columns together, that's another way to solve it. I never think of it that way. So what Gabriel is suggesting is, instead of solving it this way, why don't we solve it this way? Put the 3 columns, 2, minus 4, 1, minus 6, 7, and minus 3, 8, h, and 4, and then we solve it. Yeah, and then yes, you would have, basically you can say I have 3 variables, x, y, and z, and then I only have 2 pivots, and therefore there's one free. Yes, possible. Also for all values of h, I can get a value of x and y. Yes, correct. Yes. But yeah, I thought if you do it that way, yeah, it's the same, but it's harder for my brain to interpret. Yeah, because I'm just in my brain, I'm just thinking, can I use different combinations of x and y to form my last column? So that's easier. Okay. Anyone else? Okay. If no, then I think, yeah, we are done. Maybe I will post it up very soon, and then you can see the rest of tutorial 1, question 1 to 6 in the online as well for my last class. Okay, thank you very much. Goodbye.